Thank you so much. Hi, everyone. Welcome back to our Play All Day webinar series. If you're just joining us for the virtual conference, my name is Laura Masterson. I'm the Community Manager here at Typesafe. A couple of housekeeping items before I hand the stage over to our next presenter. As a reminder, we will be posting all of the recordings from this webinar on our website and YouTube channel. You can look for those in about a day or so, and we'll also be sending out the links to all registered attendees. If you have questions throughout the webinar, I will be manning the Q&A section, and I'm going to be reserving some technical questions for the presenter at the end. So with that, I'm going to hand things over to Henry Nissenbaum. He's the Director of Engineering at the Huffington Post, and he's going to be presenting to you about playing with Akka. Thank you, Henry, for joining us today.
Well, my pleasure, Laura. Thank you all for joining. So by way of introduction, my name is Henry Nissenbaum. I'm with HuffPost Code, and we're the engineering arm, the software engineering arm of AOL's Huffington Post. What I'm going to be doing is talking to you a little bit today about our use of Play here at the Huffington Post, and more specifically, how we've integrated with Akka for handling some of the more complicated cases that we come across, those that are not straightforward web request and response type of uses. So a little bit of background on HuffPost Code. Huffington Post is now 9 years old. We just passed the anniversary a few days ago, I think it was. Happy anniversary, Ariana. And the code we rely on, certainly that we relied on about a year ago, was what was described as a legacy code base. It was a large monolithic code base built mostly with PHP and even had some bits of Perl here and there. All of the various components that went into the Huffington Post, the editorial CMS, the ad revenue CMS, page rendering for desktop and mobile, a number of reporting tools, APIs, other bits and pieces, were all one big chunk of code. Now, as you can all imagine, that didn't work that well. It started out making a lot of sense, but as the years progressed and things changed, it became less and less manageable. And some heroic efforts were required on the part of the engineering and the deployment teams to keep that whole system up to date and working. An amazing amount of caching at different levels were required to keep everything running smooth. Now, what happened was over these past 9 years, as the Huffington Post has been successful, is things have changed from the initial needs. And I pulled up some of the latest statistics. You'll see them on the screen there. These numbers are accurate, if a little bit imprecise. We have now about 1 bazillion page views per day and just over 2 gazillion unique visitors. We also have a large number of partner additions. These are partner companies in different parts of the world. So we now have, I think, somewhere about 10 international additions, and that number is growing, each of them with different integrations with ad servers and other concerns. We also have more content contributors than the dozen or so editors and writers that started the Huffington Post, and not all of whom are inside the Huffington Post. They're not all part of the Huffington Post company, and many other ways of engaging readers. So the real point I'm trying to get across is that there's a lot more to the Huffington Post now, much greater needs. The kind of performance and concerns that we had 8 years ago are not the ones we have now. The kinds of engineering team and feature needs we have now are not what we had 8 years ago, and we need something different. And what we need more and faster. We need better performance in terms of latency and our ability to handle load. We need to be able to manage our operations more efficiently. Having one giant code base doesn't work when you have that many services built into it. We need to be able to deploy them individually, scale them appropriately. Some services need more, some services need less. Some of them change on a day-to-day basis. And we need faster software engineering. And we need our teams to be able to work on new features isolated from others. We need to be able to lower the amount of time we spend on maintenance and the amount of and the intervals it takes to satisfy certain problems, just in terms of isolating faults and fixes from different parts of the code. I'm sure as I describe this makes sense to most people. If you've been involved in the software business for a while, you'll recognize that the kind of infrastructure we had grows organically and makes a lot of sense as to how we got there, but it's not how we want to continue to operate. So what we need is independent services. We have many different pieces of the code, and they need to be able to be built separately, run separately, managed separately. We need more maintainable and slight pun intended there, type-safe code. PHP can do a lot of things, but when you're building a large piece of software engineering, having the guarantees that you get with compiler time guarantees makes everyone's life quite a bit easier and just provides for a much better software engineering experience. And we need scalable services. We need to be able to scale some of these services very quickly and for really internet scale, for millions and millions of users, nonstop, 24 hours a day, 7 days a week. So what we're looking for is a platform for the future. Now, what happened was about a year ago, recognizing all these considerations and the goals for the future, the HuffPost Code team, leadership team here, made a decision to start moving to Scala as the programming language of choice and to use some of the frameworks that were available in Scala, ideally to get better performance, better scalability. And since that decision was made, we've firmed up some of the other auxiliary decisions. We decided to go and use the Play framework for our web applications, and I'll talk a little bit about some of those choices and where we're using Play. And then as that decision was being carried out, that led us towards using more Akka for handling the background services and for orchestrating some of the more complex web applications, web requests, and responses that need to be handled in the background. And also part of Akka is that messaging. So having that, what I described as that orchestration and messaging layer built into Akka proved very useful in a number of cases. And this is very much the framework that we're working with today. This is a work in progress. Some of the things I'm going to show you are in production today. Some of them are in development, and some of them are in planning. But this is the platform that we're working with on a day-to-day basis and will be living with for quite some time, we expect. So first, a couple of words about the type of Play applications we use. We've got a lot of web applications, some small, some very large. And our web applications are pretty much split into two. A lot of our internal applications are single-page web applications with an Angular front end. They're used by our editors, our business folks. They're more like real applications, desktop applications for the CMS, for handling ads, for reports, and things of that sort. Our consumers tend to see what are more classic MVC multi-page applications where we're using Play Scala templates and some of our own homegrown templating schemes to render the pages that consumers see. In addition to web applications, we've also have a number of RESTful APIs, internal and external, that are using Play for the HTTP layer, the authentication, those kind of services, and conversion to and from JSON that's needed for the RESTful APIs. And behind the scenes on those RESTful APIs, almost all of them are using Akka to really handle the requests. So the request processing is actually handled by a bunch of Akka actors for scalability, resilience, and responsiveness. And those are some of the things we're going to be talking about now are two cases of where we built RESTful APIs using Play at the front and Akka to do most of the heavy lifting. What I've got here is a partial picture of what we refer to as the big picture. Many of our services broken down into where they are and what they do. I'm going to give you a brief walkthrough of what this looks like, what it means. It's not absolutely necessary that you understand all the business purposes of these bits. What I really want to get across is how Akka fits into this and some of the benefits we've gotten out of it. So on the right, you'll see a couple of green boxes. These are web applications that are used by our internal Huffington Post folks. The editorial CMS and revenue CMS are two examples of that. All the way on the left, on those blue boxes, these are web applications that our consumers access, although they might not necessarily know that. The one on the top left is the core one. It's the renderer. It's generating the web pages. Right below it is a WebSocket server that is used to send notifications to either our mobile apps or the web clients as well. And the third down is a relatively small purpose-built server that allows our mobile application users to register for notification receipt. And we'll talk about that more because that'll be one of the cases that we review. What you'll see in the middle are some purple boxes, and these are web servers that are used for internal purposes. Some of them are APIs, and they're shared by multiple other components, but they're all internal to our network. And then finally, that pinkish rectangles are some of our Akka clusters that serve some very specific business purposes to satisfy some needs. And those two that I've got there on the diagram are going to be the two cases that we reviewed today. Two code names we have, our Modulus actor system and our Fiji actor system, and I'll walk through those with you. What you'll see at the bottom of all this is the actual persistence layer. So at the end of the day, all of these systems are involved in saving or displaying data that is persisted either in traditional databases such as MySQL or a document store. We use Mongo, and we use Elasticsearch as well for finding things that we need that's either stored in some of those data stores or some other purposes as well. What's not shown in this picture are other web services that we rely on, either other AOL services or other third-party services, although we'll be talking about one of them when we get a little further on and we talk about Fiji notification service. We'll come back to this at the end just to kind of sum up. Now, I know people have been talking a lot about the Typesafe platform, and that means you've probably heard something about Akka. I don't quite recall if there's a session on Akka before this one, but what I'm going to do is provide you with an extremely painfully brief introduction to Akka, just to give you a sense of what we're using Akka for, what we're getting out of it. If you haven't done any research with Akka and you're using Scala, and it's certainly worthwhile doing. The documentation is pretty strong, and some good courseware as well. So Akka allows us to create actors which are pure objects. And what I mean by that is they interact with the outside world via messages. They accept and process messages, and they emit messages to talk to other actors and other related systems. These are asynchronous in that each actor processes messages asynchronously and independently, and yet they serve to synchronize a whole system. And that's kind of a nice paradox of Akka, is that very often you need to manage access to a resource or the like. And because Akka actors process one message at a time, exactly one message at a time, you can control the synchronization in a very clean way, and which is where you get most of the benefit of Akka as compared to trying to roll your own with multiple threads distributed over various systems. Akka actors are distributed. It's built into the infrastructure. You can set up clusters. It's more configuration than coding to set up these distributed Akka clusters. They're supervised, so when things fail, there's a built-in and consistent mechanism for recovery. And they're decentralized. So as I mentioned above, this is a message-based system. It includes its own mechanism for communicating those messages, so there's no need for an underlying messaging infrastructure, which is itself a single point of failure. So with that very brief introduction, I'm going to talk to you about how we're using Akka, and in particular these two cases that I want to review. I like them because they're orthogonal uses for Akka. In one case, we're using Akka to build a very responsive web service. This is a RESTful API, and what we're using it in the part of our system where a rendering engine needs advertisement codes that it's going to put onto a web page. So we might need to get 3 or a dozen different advertising codes, and it varies depending on the kind of page, the edition that we're rendering, the time of day, etc. And in this particular case, that rendering engine needs a guaranteed response time. There's a certain budget that is allowed for it to be getting this information. Let's say it's on the order of 100 milliseconds. And once that time passes, it needs to do something. And here we're building a system which is very responsive, and it provides those guarantees with a fallback when the guarantees can't be met. The other example we're going to talk about is one where our mobile application users register for event notification. If you use the HuffPost mobile applications on either iOS or Android, you can register for events. It's kind of nice. I know probably the last event I noticed went out yesterday, something about, at least if you're in the U.S., about the guidelines that the EPA is sending out. But here, we need resilience. We need that when users click those buttons in that mobile app and the message gets sent, that the registration completes successfully. It's not so important as to how long it takes. Whether it takes 100 milliseconds or 10 minutes, for the user's point of view, doesn't really make a difference. So what we want to do is guarantee resilience, less concern about timeliness. And so what we'll do is we'll walk through these two cases, and I think they present a good picture of how Akka can handle many of the more complex needs we've got that might be front-ended in a web application. So first, the case that we're talking about for rendering advertisement code. Internally here, we call it Modulus, and it's a RESTful API on the Play framework used for page rendering. So as I said, our renderer will hit the Modulus API and say, give me all the advertisement codes, what we call the flights, for these placements. These basically holes on the web page I need to fill with revenue or other related items. Now, if someone had come and asked me to build something like this a couple of years ago, I might have done something along these lines. I've got the data in an Elasticsearch and in a MySQL database. I need Elasticsearch to be able to find what I'm looking for quickly, and then MySQL to get the full set of data out of it. I might cache some of the data so that I'm not always hitting the database. And so what I might have done is built a servlet where it would take the request, figure out what the search is, make the search from Elasticsearch, take that response, check and see if it's in the cache. If it's not in the cache, make multiple queries to the database, assemble those results, if necessary, update the cache, and then marshal the response back to the HTTP client that started it all off in the first place. And this kind of approach works, but it becomes very complex and very difficult. Any one of these lines can fail. There's all kinds of things that can happen along the way. It's very hard to manage this so that if we get hit by a storm of requests, we don't start to deteriorate badly. And we now have better ways of doing it. And one better way of doing it is the way we have, and this is in production and in use, where we use Akka to orchestrate and manage all this and to assure us of our responsive requirements. So what you see here are, on the right in those gray boxes, are the resources that are holding the actual data. So our Elasticsearch, a really Lucene search engine, MySQL holding our data, and some EHCache caching to cut down the number of times you actually have to hit the database. Those blue boxes are all of our Akka actors doing the work. We'll see on the right set of actors are actually actor pools. And so what this does is this allows us to manage the number of requests at any time that are hitting the Elasticsearch engine or any of the databases. There's no chance of us blowing out the connection pool to the database. We have a very simple mechanism of controlling that because we only have, let's say, 100 of those flights actors, so we'll only have 100. We can't use more than 100 database sessions at one time because, as I described, each actor is processing exactly one message at most at a time, and that we can't go over. The core to this is the actor all the way to the left, the flight searcher, and there's a single one of these per node in the cluster, and it's orchestrating the request and doing all the work. So what I'm going to do is I'm going to walk through what this has to do. And again, the exact details are only terribly important to our particular need, but hopefully it'll give you a picture of how this relatively straightforward orchestration can be worked out and in a kind of a nice, clean way. So what happens is an HTTP request comes into the Play application. The controller gets this request, and what it does is it sends a message to the flight searcher. Now, in this particular case, we need to respond to the HTTP client with the data. So all of this has to happen, as I described, in a pretty brief period of time. What the flight searcher does is it starts off by making a request to the Elasticsearch, the Elastic router, by which it gets access to the Elastic actors. At the same time, you'll notice it actually sent up there a flight search timeout message to itself. We'll come back to that later and see what that means and how it gets used. The Elastic router passes the message off to the Elastic router passes it off to an Elastic actor. Elastic actor makes the call to Elasticsearch, gets the data back, and in this particular case, we've got a success message coming back. Other cases, it would fail, in which case the flight searcher would have to handle that. In this case, we'll deal with a relatively simple case where everything's working right. We got the data back. The flight searcher is now going to hit the cache and ask if it's got the data. In this particular example, what I'm going to say is the cache response is it's empty. Otherwise, this story would be cut brief, and it's just not that interesting. And so the flight searcher realized, okay, I've got to get the data for flights and modules. And it'll make two requests, two messages, one to the flights router, one to the modules router. And here we get a little bit of parallelization. These various actors can be running on different machines. These requests are made in parallel in a very simple fashion. 2 lines of code, 2 messages sent. And now, as far as the flight searcher is concerned, it's just waiting for all the data to come back. The various actors and interactions with the MySQL database can happen, and at some point, in this case, I'm showing the modules actor responds first, and then the flights actor. The order is unimportant. The flight searcher takes care of all that. Once it's got all the data, it says, fine, I'm done. It sends a flight search success message back to the Play controller, and in Play, this has all been sitting there quietly waiting in the future for this message to come back. The future now receives that message and responds to the HTTP client, waiting not so patiently in under 100 milliseconds, for most cases, and that's of course a deployment configurable parameter, but I like using that as just an example when speaking. At the same time, the flight searcher also updated the cache as a separate asynchronous activity, as things were going. Again, a real simple thing to manage. Now, you'll recall, and you'll see it there, when we started this thing off, the flight searcher sent itself a timeout message. And the reason for that is, during all this interaction with the various actors and Elasticsearch and MySQL, some things could have gone bad, or they could have taken too long. And if that had happened, the timeout message would have gotten back to the flight searcher before they all had finished. In which case, the flight searcher would have forgotten about everything else and said, never mind a flights actor, a modules actor, I no longer care about what you're sending back to me. I'm going to have to tell the Play controller we didn't make it. It failed. And with enough information so that the Play controller now knows how to send back a default response. The default response will go back to the HTTP client. Now, what's not going to happen is the advertisement that we wanted showing up is not going to show up on the page, but the user will not be waiting. So they'll get some default display in those various spots that should be showing paid advertisements. We'll have missed out on that little bit of advertisement, but the overall rendering engine will have worked satisfactorily. Okay. And that is our example. And of course, I removed a lot of the little messy details. And what I'm going to do, I think, at the end of this, allowing for time, is showing you just a little bit of code to show you how Play integrates with Akka. It's really quite simple and clean. If you know a little bit about Akka messaging and perhaps a tiny bit more about using futures, which you should if you're using Play, you'll see how very little code now cleanly that integrates. So we'll come back to that towards the end. But first, I want to review the other use case, and as I described, it's rather orthogonal. Here, we have our mobile application users clicking through the settings. They register for event notifications on the various topics that they're interested in, and we need to make sure that we accept that request and process it. In some cases, it's even possible that timeliness could be 2 hours later, and a human being is even involved in straightening things out, as long as we don't lose the data. So let's take a look at how that might happen. And this is a project that was named Fiji. And by the way, about these project names, I had nothing to do with them. They got named before I joined the company. I don't know how they came about or who named them. I guess it's different teams, and they just came up with their own naming schemes. So Fiji, and in particular part of Fiji, we have our mobile alerts registration. What does this look like? Well, again, we've got a pile of actors. In this case, if you look all the way on our right, what we're really doing is we're using a service from Amazon. Fine folks of Amazon have a service called SNS, which provides a way of sending messages to iOS and Android devices. They've abstracted that out, and we can send at a very low cost. We tell them what messages to send to what endpoints, and they do it for us. Now, behind all that is you've got to tell Amazon about these devices, put them into various groupings, quite a bit of bookkeeping that has to go on between Amazon and in our own system, keeping track of that. So what this application is all about is telling Amazon what we need to tell them, finding out what topics we've got, who's in the topic, managing these device endpoints, and keeping track of the bookkeeping in our own databases. And that's what this pile of actors are for. Now, a couple of notes here. If you look at that Amazon SNS, we have an SNS actor behind which is our single SNS client. And what this does, you'll note it's a single actor. This allows us to control access to SNS through a single actor. And one of the things that Amazon does is it restricts the rate at which you can pester them with messages. So we've got a single actor. We put in a throttling mechanism to control how many messages, at the rate at which we hit them with messages, and that becomes a very easy thing to manage. It's all in one place, and it's all very resilient. Should that SNS actor fail for whatever reason, it can get restarted. And you'll see a similar actor, as we had seen earlier, interacting with a MySQL database, a data actor. And the one in the middle, the topic proxy actor, kind of a complicated name, is there to facilitate some rather complex logic on interacting between the SNS actor and the data actor. I won't bore you with the details, but for us it's a good case where we have some complex logic, needs to be encapsulated in one place, and it interacts with three different things. We can build it there. So first, let's look all the way at the left. We've got the play controller, as we had seen before, and now we have our device registrator. And this is our mother of all actors, and it's keeping track of all requests. And because it's got to be resilient, it controls how many requests we're handling at any one time. It's an engineered number. And it also manages failures by retrying, and even, if necessary, allowing a human to be involved through the play controller and another interface to look at those failed requests and update them if necessary. We won't go through all those details, but we will go through some idea of what's happening. The key to this is the endpoint actor, which we're going to go through in some detail, give you a sense of a much more complicated actor. So what happens, one of our mobile applications makes a request, comes in by HTTP to the play controller. The play controller sends a request message to the device registrator. Now, the device registrator can either accept or reject the request. In either case, the response is very, very fast. So because we want to get back to the client right away and let them go on their way. And so let's look at a case where we actually have a relatively simple, the play controller makes a request, and we're going to get a successful response back to the client. Because what the device registrator is doing is it's going to create a new endpoint actor just to handle this request. And again, there's a limit to the number of these we'll have outstanding at any one time. If we ran out of resources, the request would go onto the wait list. In this case, It's actually creating a new endpoint actor, and we're going to follow along the life of this endpoint actor. And what I'll do is I'm going to skip through some of the details toward the end. I'll either start talking very quickly or skip some of it because it's probably less interesting to you if you're not part of the Huffington Post. But what it's important, though, is that we create the new endpoint actor. The device register sends the play controller back the accept message. We're good. Play controller sends back the message. So now the mobile app user believes that they've registered. They don't know that we haven't finished doing all the work yet, but they can go on their way and read our articles on their phone. In the meantime, what's happened is the endpoint actor has this newly created endpoint actor has started the work going by sending a message to the SNS actor to create the endpoint. Now, one of the really nice features of Akka, which I'm not going to be able to describe, but it's worth learning as you're working with Akka, is the ability of an actor to take on many states. This particular endpoint actor has to do rather complex work, but at any one point, it's in one of, I think, 5 states we've got for this actor, and there's very little complexity at each state. Taken as a whole, it could be unbearably complex, but if you look at each state, and being able to have an actor move from state to state makes the code real clean. I'm going to show you just a little snippet of code that a rather complex diagram ends up being very few lines of code and is very easy to express in an actor. So let's look at that. So now the endpoint actor has, well, we no longer care about the play controller or the HTTP client. We're on our own satisfying this request. We sent the message to the SNS actor, and we go into the endpoint create state. Now, there's just a few messages we're expecting and a few we might send out. We're waiting for a response back from the SNS actor. We get it, and we move on with the next couple of steps. We send the SNS actor to set some attributes, to actually set some parameters and values back at SNS. We also, at the same time, send ourselves a message looking up whether or not we've got a subscription already. And with that, we change states to the endpoint subscribe state. Again, you see that one state was relatively simple. Now the endpoint subscribe is waiting for a couple of messages back. And the ordering, it shouldn't matter. Remember, these are all asynchronous and can respond in any particular order. We get the subscription lookup response, in which case we unsubscribe from the SNS actor. The SNS actor responds to that message. And then independent of that, actually responds with to the set attributes message that we had sent earlier. The important thing is that all that interaction is complete, and now we send another message, topic lookup, and move on to the next stage. Again, this details of this are probably really only interesting to me and 2 other engineers here at Huffington Post, but the really nice thing about it is we're able to remove all this complexity and deal with it in very small pieces, which I'll show you very briefly. Now, here's a nice case in that we get to this topic state, and here we might have to work 2 different ways, depending on whether that topic lookup message that we sent earlier returns with data or nothing. If it returns with nothing, you can see the none there, well then we've got to add the topic, wait for the response to come back from the data router, save the entities, and then move on. Now, an alternative case might have looked something like this. Here we're back at the beginning of the topic actor, and here we actually got something back from the data router. And in which case, we do something different. We have to hit the topic proxy actor, whose purpose I will not go into detail on, and it goes through a whole bunch of activities in dealing with the database and the SNS actor as well. But what I wanted to do is just show you we've got these 2 relatively complicated cases going on, but really very little code. So what I'm going to show you is the receive method, really the receive function that is dealing with that. And it's really just the code in blue that you're seeing here. So when we go into the topic state, we're using this receive function, and there's 2 cases. We either get a topic lookup response or a topic add response, and the topic lookup response deals with whether it's none or some, with either sending a message or an alternative message and changing state or not. You can glance through the code and see, again, I don't want to walk through line by line. I don't think it's that valuable. If you're familiar with Akka messages, this will make sense. If you're not, the exclamation marks, the bangs, are are the Akka tell, the sending of a message, and the context.become means change state. So no matter how we slice it, we'll exchange a couple of messages and end up changing state to our subscribe state. In other words, moving on to the next state where we have a simpler level of logic. Every one of these receive messages, these receive functions, that we've got are less than a screen full of code. And so at each step, we're not talking about a great deal of complexity. And what I'll do is I'm not going to waste too much more time going through all the details, but we've got the subscribe state, more things going on, more messages are happening between actors, responses, and we finally moved to our final subscribe SNS topic state. And I won't even bore you with the details. It just stuff's going back and forth between the SNS actor and the data router, all to keep track of this bookkeeping until it's finally done. And the endpoint actor sends back its response to the device registrator, and that now handles that, cleans it off of its ongoing list, and it's done. And that actor now goes away. Once that's done, once we're kind of looking away from handling each one of these actors, the play controller is still interacting with the device registrator and allowing our administrators to see what's going on. So I won't go through those details, but there's quite a bit more messages between the play controller and the device registrator to see what's in the wait list, to see what's in the fail list, and if they need to interact with failures that have failed some number of times, they can do so, clean up those registration requests, and make sure they complete successfully. Now, as I had mentioned, I see we don't have a whole lot more time, but I just want to show you this. Again, to give you a sense of how little code and how clean this code is to set this up. What I'm going to do is I'm going to kind of walk backwards as to what it takes to connect play with Akka. Here I have a function called submit search request, which, as the name suggests, takes a flight search request, which is something we build out of the HTTP request that comes in, and it's going to return a future of a flight search response. So what it's doing, and you can see that in that little block of code, that it creates a message, which is simply a flight search message which encapsulates the request, and that question mark, which I put in blue, again, if you're not familiar with Akka, this is the Akka ask. And what this is it sends a message, and now we'll wait in the future for the response message to come back from the actor. And what it's waiting for is a flight search response message, so you can see that map too. And the end result is a future of a flight search response. We send the request, we now have a future waiting for this message to come back from the Akka actor. And this is the code that we use for this modulus case that I talked about earlier. So backing up a little bit, this function is used in turn by the method that actually gets the flights. So again, here's a bit of code, and I won't walk through all the details of it, except to say what you'll see is that we made the search request, we got the search that future, and now we're pulling the data out of it. If it's a success, we will convert it to JSON and send it back to the play controller, which I'll show you in 1 second. If it's a failure, we do some other handling. We create, we log it, we create alternative data to hand back to the client, and move on. But moving back up the stack to the actual controller action, and this is where we have that async action. Again, very simple bit of code. We call the get flights method that you just saw, and map that future to a result that gets handed back to the client with just a little bit of formatting to send back the JSON data. And that's it. A pretty easy setup for connecting between your play controllers and Akka actors in the environment. And with that, I'll go back to the big picture just to go back and give you that context. So what we saw happening here, to wrap it up just a little bit, and then we'll stop and see if there's any questions, is that HuffPost renderer hitting the module service or the modulus, and the modulus actors responding in time to get the results back in the time needed, success or fail. If they can't do it in time, they do it anyways, even if it's not optimal. And then our Fiji actors, I showed you just the registration interaction between that registration server on the bottom left interacting with Fiji actors. There's a similar set of actors, which are in some cases even more interesting, which we use to send messages to those registrants when they come up. And if you use the Huffington Post mobile applications, you'll have seen some of those notifications if you had registered for it. So with that, that's all the slides I have, just in the nick of time. So thank you very much for listening.
Thank you. Appreciate your time today. That was great. I think we do have a little bit of time left for some questions. Let's just go over there and open them up. First question says, so you mentioned using a WebSocket server for public web clients. How are you managing to make this cross-browser compatible? Have you looked at casing WebSocket Gateway, and if so, would you recommend it?
All right, I will give a partial answer to that because I don't know the full answer. We actually have our own homegrown WebSocket server that we built in Erlang. It's built a couple of years ago, and I don't know the details of how it's cross-browser compatible, but I do know that it falls back when there's no WebSockets to a polling system. I'm just not that familiar with it, but I haven't seen any mention of casing, so I know we haven't looked at that. And I see another question from Sean Brady. What happens when singleton actors fail? Well, that's a great question. It depends on the actor and what the actor needs are. A lot of cases, they simply get restarted. And the only thing that's happened is the message that they were processing gets lost. In, for example, the modulus case, should that happen, which sometimes happens with database actors, is that the result will be a timeout, and we handle that lost message without a problem. The most challenging case for that is on the Fiji side. In that example, if that registrator actor, the one that's keeping track of everything, fails, well, then we've got a problem. And so we're actually in the process of integrating, using the Akka persistence to manage that, so that should that actor fail, we don't lose everything. Okay.
Great.
Let's see. Another couple of questions. How do we test endpoint actors? That's a great question. I'm not going to be able to do a really good job of answering that, except that, yes, we have unit test cases that all of the services that the actors use are abstracted away. And so we have test code that we hand the SNS actor instead of the actual SNS endpoint. We have our own little SNS service, and so we build a mock that handles that and does all the interaction in place of actual SNS. There was a question here about how much state do we use in Akka actors? Well, as much as is necessary. Depends on the case. Some of the actors, for example, that Fiji actor, the Endpoint actor that moves through the various states, there's quite a bit of state keeping track of everything that's going on. And that's okay. This is a purpose-built actor just for this, and when it's done with this job, it gets tossed away. So some actors have quite a bit of state in them. It's not always bad to use vars in Scala. There are some excellent cases in Akka where you're going to want to use that, and because they're so nicely protected by the behavior of Akka and only processing one message at a time. And there was another question. Go ahead.
Yeah, let's do one more question, and then we need to wrap up.
All right. There was a question about actor communicating with TCP servers like XSocket server. There are all kinds of integrations that you can either roll your own, or if you look at the Akka docs, you'll see there's quite a few plugins. There's a pretty decent way of connecting Akka with messaging systems, which usually gets you most of the way there if you need to interact with other parts of the world. And with that, thank you all for listening.
Yes, thank you. We're going to cut the line here and head into our next presentation by Guilt Group. So we will see you on the other side. Thanks again, Henry.
You're welcome.